Hi and welcome to this quick presentation about performance improvements in JDK 8. My name is Staffan Friberg and I'm the technical lead for Java SE Performance at Oracle. The Oracle Safe Harbor statement. While the release drivers for Java SE 8 have been about evolving and extending the Java platform, we have continuously been working on improving the performance of Java. I'll cover both performance improvements done to existing features that you can take advantage of instantly with your current applications, as well as work done to make sure new features have great performance. Scalability has been one of the key targets for JDK 8, all the way from the language updates with Lambda down to low-level memory management in the VM. As part of this, the Concurrent API has gone through a major revision in JDK 8. Fork join now takes advantage of the fact that the VM can be made aware about fields that are frequently updated by different threads and automatically optimize the memory layout of these fields to avoid false sharing between CPUs. Fork join has also been improved to better handle small and short-lived tasks, as we expect this to be a common use case for Lambda, and it serves as the backend for parallel streams. The Atomics API have been improved by using compiler intrinsics that select the optimal assembly instructions depending on the current CPU architecture. And the new adder APIs provide scalable counters that can efficiently be used concurrently by multiple threads. While not everyone might be aware about the different compilers in the virtual machine, there have historically been two different compilers available: client and server. As the names imply, they have been focused on client and server workloads respectively, with the client compiler focusing on footprint and fast initial execution, and the server compiler more focused on peak performance. With the tiered compilation, we aim to combine the strength of both compilers, achieving the fast startup and shorter time to performance of the client compiler, while making sure we still get the same high peak performance of the server compiler. This will shorten the startup of large applications as code will be compiled earlier, and client applications or short-running applications will get better performance as the server compiler will kick in and optimize the code and the critical path. I don't think there's any Java developer who hasn't run into the VM exiting with a permgen out of memory exception. This tends to happen if you're running an application with a large or a dynamic set of classes, and the permanent generation was where the VM stored internal native data structure, such as class information. It added an artificial limitation on the amount of memory that was available for loaded classes, and you could only configure the size on startup. Set it too low and you would run out of memory. In JDK 8, the permanent generation has been replaced by a feature called metaspace, and this is much more than just a name change. This is a complete rewrite of how the VM internally handles native data structures. Rather than having a fixed pre-allocated area, the VM is now able to expand when required, and the native memory usage is now only bounded by the maximum process size. And with the new metaspace, we extended an experimental feature called class data sharing. Class data sharing allows the VMs to share loaded JDK classes between all Java processes on the same host. This helps to reduce the startup time as well as the total memory footprint on the machine. And as mentioned, this feature is currently experimental, but please do try it out and let us know if you find it useful. Used InvokeDynamic method handles as part of JSR 292, which enables dynamic languages to run more efficiently on the VM. InvokeDynamic allows dynamic linking of a call site as part of the first execution of a call. And after linking, the VM has full knowledge about the call site. And this means the VM is able to inline and do other optimizations in a way not possible when using reflection. For JDK 8, we spent a lot of time and effort to optimize InvokeDynamic from the initial JDK 7 release, as we have learned much more about how it's being used by other languages. We also improved it for a couple of new features. For Lambda, we're able to avoid allocation completely for non-capturing Lambdas, and the compiler can incrementally inline method handles, which helps improve Nashorn performance. Nashorn is a replacement for the aging Rhino JavaScript engine. It also serves the purpose of showing that InvokeDynamic can be used to run dynamic languages on top of the VM with great performance as a result. And Nashorn doesn't disappoint when it comes to performance. It's 3 times faster than Rhino for almost all benchmarks in the Octane suite. And this is just the beginning. We have already pushed further improvements as part of JDK 8 updates that doubles the performance of a couple of these benchmarks. InvokeDynamic plays an important role in Lambda. By using InvokeDynamic, it was possible to decouple the implementation and execution of Lambda from the bytecode. Any required methods and classes are generated on the fly by InvokeDynamic, making sure that the JDK and VM can be optimized without requiring developers to recompile their Java code. Lambda execution can be split into 3 separate steps: linkage, capture, and invocation. Linkage is a one-time cost of setting up a Lambda expression. Capture is the cost of creating a specific Lambda instance. And invocation is the execution of that Lambda expression. And here you can see the cost of linking and capturing Lambdas compared to using init classes. The reason why we're comparing to init classes is that they are commonly used to solve similar constructs in Java today, and they were also evaluated as part of the design phase of Lambdas as a possible solution. As you can see, even in our first release of Lambdas, the performance is on par or faster than using init classes, and we expect to improve this further in update releases. Okay, JavaFX is included as part of the JRE from day one, and the graphics pipelines in JavaFX have been significantly optimized in JavaFX 8 compared to JavaFX 2.2. Our performance testing and benchmarking show rendering shapes, UI interactions, and node layout to be up to 3 times faster on modern GPUs, and on low-end devices or embedded devices with only a software pipeline, you can see up to 10x speed up. For developers and users of JavaFX, this translates to higher frame rates and the ability to run and create more advanced UIs. Time to go through a few of the highlights in this presentation. There have been performance improvements all across Java libraries and the VM. A couple of improvements worth mentioning are to the hash map and concurrent hash map that now use a tree structure to avoid long lists. This makes the bin search faster in the case of a large number of collisions. We have also made sure that some of our caches are more scalable by utilizing concurrent hash map instead of a standard synchronized collection, and also use double check locking to reduce synchronization. When putting all of these improvements together, we get pretty impressive performance improvements with JDK 8. Thanks to scalability improvements in the JDK and VM, we see close to a 50% boost in the max JOP score in SpecJBB 2013. And similar to what we did in JDK 7, we expect to improve this further in updates of JDK 8. Thank you for watching this presentation about performance improvements in JDK 8. If you're interested in any of the new features in Java SE 8, you have several presentations, tutorials, and demos available. Make sure you download and try out Java SE 8. Thank you.